Good morning, champ. Last time we used the Lagrange multiplier method to find extrema when there was one constraint. But in many real problems, there are multiple constraints, like when a point has to stay on the intersection of two surfaces. That's where the generalized Lagrange multiplier method comes in. It works exactly the same way, just with one multiplier for each constraint. Suppose we want to optimize a function f of x, y, and z, subject to two constraints, g1 of x, y, and z equals 0, and g2 of x, y, and z equals 0. Each constraint restricts where our point can move. Two constraints in 3 dimensions mean the solution must lie on the curve where both surfaces intersect. At the optimal point, the gradient of f lies in the same plane as the gradients of both constraints. In symbols, nabla f equals lambda 1 times nabla g1 plus lambda 2 times nabla g2. Here, lambda 1 and lambda 2 are the Lagrange multipliers, one for each constraint. They tell us how strongly each constraint affects the optimization. That equation means all 3 vectors, nabla f, nabla g1, and nabla g2, are coplanar. That plane is tangent to the constraint curve where the extremum occurs. To find the extrema, we solve this system. Nabla f equals lambda 1 nabla g1 plus lambda 2 nabla g2. g1 of x, y, and z equals 0, and g2 of x, y, and z equals 0. This gives us 5 equations for the 5 unknowns, x, y, z, lambda 1, and lambda 2. Let's go through an example. We want to find the extrema of f of x, y, z equals x plus y plus z, subject to the 2 constraints. g1 equals x squared plus y squared plus z squared minus 1 equals 0, and g2 equals x plus y minus z equals 0. So we're looking for the highest and lowest points where the plane x plus y minus z equals 0 cuts through the unit sphere x squared plus y squared plus z squared equals 1 squared plus z squared equals 1. Compute the gradients. Nabla f equals bracket 1, 1, 1 bracket. Nabla g1 equals bracket 2x, 2y, 2z bracket, and nabla g2 equals bracket 1, 1, negative 1 bracket. Now set up the Lagrange condition. Nabla f equals lambda 1 nabla g1 plus lambda 2 nabla g2. That gives 3 equations. 1 equals 2 lambda, 1x plus lambda 2, 1 equals 2 lambda, 1y plus lambda 2, and 1 equals 2 lambda 1z minus lambda 2. From the first 2, we can see that x equals y. Substitute that into the plane constraint x plus y minus z equals 0. That gives 2x minus z equals 0, so z equals 2x. Plug this into the sphere constraint, x squared plus y squared plus z squared equals 1, which becomes x squared plus open parenthesis 2, x close parenthesis squared equals 1. Simplify, 6x squared equals 1. So x equals plus or minus 1 over the square root of 6. Then y equals x and z equals 2x. That gives 2 points. 1 over square root of 6, 1 over square root of 6, 2 over square root of 6. And its opposite, negative 1 over square root of 6, square root of 6, negative 1 over square root of 6, negative 2 over square root of 6. Evaluate f equals x plus y plus z, which is 4x. At the positive point, f equals 4 over square root of 6. That's the maximum. At the negative point, f equals negative 4 over square root of 6. That's the minimum. Geometrically, the first constraint is a sphere. The second constraint is a plane, and their intersection forms a circle. Our extrema are the points where the plane f equals constant just touches that circle, tangency again. At those points, the gradients of all 3 surfaces lie in the same plane, showing the perfect balance of the Lagrange condition in 3 dimensions. And we can go even further. For a function f of x1, x2, all the way to xn, with m constraints g1, g2, up to gm, we write nabla f equals lambda 1 nabla g1 plus lambda 2 nabla g2 and so on, up to lambda m nabla gm. and each constraint g1 equals 0, g2 equals 0, and so on. Each new constraint adds a new multiplier, one more equation, but the idea never changes. Parallel gradients mean tangency, and tangency means optimality under restriction. So, multiple constraint Lagrange multipliers take the same elegant idea and extend it to higher dimensions. Each constraint adds its own multiplier, keeping the gradients aligned and the motion confined to the allowed region.